Let it begin. Oh, by the way, guys, so today we're going to be basically talking about probability, right, and how to use this in various scenarios. Uh, One thing I was planning on doing is double counting, but I don't think I'll be doing that because there's a lot to cover in probability, to be honest. But we'll go there if we have time, right? Yeah, so probability. So just to, oops, everybody can see the screen. Echo. Oh, okay, shit. It's at zero volume. Why is the sound coming out of this thing? Give me a moment. Is it
Actually, I
better
don't
now?
think there's any echo.
All right. Okay. Just let me know if there's any issue at any time. And guys, feel free to talk. Okay. Yeah. Yeah. So we're going to talk about probability and how you can use this in various scenarios. So I'll spend like the first, I don't know, first 5-10 minutes. We'll just set up like all sorts of basic definitions so that there's not that much theory, and in combinatorics there's not that much theory in general, but we there is a slight amount of theory that we need to set up, so we'll do that. Right, so first, what's a random variable? A random variable, my handwriting is horrible. I'm really sorry about that. A random variable, say x, is a variable that can take various values. Say x can be the whatever the dice is showing. So dice. So if x is that, then x could be 1, x could be 2, x till 6, and so on. A random variable could be say -1 and 1 for heads or tails, something like that. A random variable can be anything. It's just a variable that can take different values according to whatever event we're talking about. And a probability, and we generally assign probability that a random variable is something. For like a dice, the probability that dice px equals 1. This notation is 1/6, right? I hope that this notation is intuitive and not too complicated, right? So for this is for
Yeah,
this
this notation is
normal.
quite intuitive.
Yeah.
Yeah.
So this will be 0 because a dice can't show 8, right? Yeah, so that's what random variable and probability means. Now the more a definition you might not have heard of is expected value, and for anybody who has heard of it, just give me a we'll get to the problems, etc. So give us 5 minutes. So expected value. So expected value is also this really intuitive thing. um, Expected value of a random variable is like the average of all its possibilities, right? So for like a dice, the expected value of the output is, say, 1 plus 2 plus 3 plus 4 plus 5 plus 6/6, the average. you know um like, is that clear? Like, basically what expected value is. For example,
Yeah.
Yeah.
I could ask you something like, what is the expected number of heads uh, when you flip 2 coins?
One.
Okay. And why is that true? And so yeah, it's not too complicated, right? We can just calculate all the outputs.
It's
Then,
like a 1 plus 1 by 2, right?
yeah. What did you say? I'm sorry.
No, it's 1 plus 1 by 2. So 2 by 2.
Right, right. That's not true. I think the way, if you write it down, you get 0 plus 1 by 2 by 4, because the probability that 0 heads, there's a possibility that there's 0 heads. 1 by 4. 1 by 4 of the times there'll be 0 heads. The one head will happen half the time, and 2 heads, you'll get 2 heads 1 by 4th of the time again. So the average will be 0 plus 1 plus 1 by plus 2 by 4, which is basically 1. Like, did you all understand what I'm saying?
Yeah.
Yeah.
Yes.
And in general, expected value can be written as the summation of probability that x is some random variable is equal to x into that x. So in this case, it's 0 um 0 into 1 by 4 plus um 1 into half plus 2 into 1 by 4. This is the expected value. Okay, and yeah, so expected value is intuitive. It's like the weighted average of everything, right? Uh, yeah. So
But
let's
but,
just
but can you say something about the significance? Maybe what is the significance of taking the average?
of the average in this
Yeah,
case.
this expected value. I mean,
So I can ask you, the average sort of gives you, okay, so the way we're going to use it in problems is we're going to use the fact that in a set, there is at least one value more than the average. Like, that's an obvious fact, right? Like, in a set, there's at least one value more than the average. So if we find like an expected value of something, which is generally an easy calculation to make, then we can make statements like there is at least one event greater than the expected value. It's like a lower bound about how something at least there should be at least one event greater than that or one event lesser than that. you know we'll get to the
oh
example.
yeah, okay,
Don't
okay.
worry about it. That's how we're
Yeah,
going to
can
use it. And it's sort of like a weighted average. And so if there's like a random variable, it helps us say, oh, see, there is at least one random variable. Like, the random variable has to go above this certain expected value at least once. So that's how we're going to use it. You will see, right? Yeah.
okay, okay.
But yeah, what you should know is that it's an average of sorts, weighted by the probability. So, for example, I could ask, here's a question. If we have, say, 100 coins, we flip them. What is the expected number of heads?
50.
Why is that true?
Like, there is 1 by 4 probability. Oh, wait. So we can just like do it. So like half of them are heads and half of them are tails. Like half the probability of one coin to turn up as head. So like 100 coins, it will be roughly 50, like expected outcome.
That's more or less true. Like, what you're saying is true, but
Yeah,
and
but then
we're
we
even
also have to like count the zeros and the
hundreds, and the one when the case where there's like
yeah.
one coin and there's two
So say, is
coins.
it like 12?
Hmm?
12?
No, the answer is 50.
Okay.
The expected number of the average number of coins. I mean, it's intuitively 50, right? I mean, why should there be any difference between heads and tails? So if
Yeah,
this
yeah, the
the
probability is
expected
1 by
number.
2.
Can I
Yeah,
tell a regress proof?
made a mistake.
Hmm?
Or can I tell a regress one?
Yeah, go ahead, please.
So like, suppose there are X heads in a configuration, like we denote by HHTT and so on, like on the
Correct.
coins.
Go on.
So suppose there are X heads.
Hmm.
The number of ways for which X heads can come is 100 choose X.
100 choose X or
Yeah.
100 CX. Yeah, go correct.
So the contribution of it in the expected value will be X times 100 choose X
Right, because this is the probability and this is the
value.
yeah. And no, we're gonna have to divide this by
Yeah. I
yeah.
meant the like.
Go ahead. Yeah, go
Yeah.
ahead.
So now we divide it by 2 to the power 100, the probability of each outcome,
Right,
and we sum it over X equal to 0 to 100.
right, and we'll get I assume 50.
Yeah.
This is a mathematical thing. Okay, you can do this. We can calculate the probability for a general like X number of heads. We can calculate all the way. We can calculate how many. So this is the basically this formula. We're gonna apply this here. So this X is this X, and the probability is 100 choose X by 2 power 100. Because say how many ways can we get one head and 99 tails? So you can get that in 100 ways. 100 choose one. So you can sum this up and you'll get 50, right? And it's intuitively 50 also. So that's just to give you an idea of again what expected value is. So is anybody not clear about what expected value is? Is it clear?
Yeah.
Right. Okay. So again, the last bit of theory. Now this is the last bit of theory we're going to be doing, and this is the whole point. And we're going to be using a lot of this, and it's an important proof. It's called linearity of expectation, and it's gonna make things like super easy. It's gonna make calculating expectation very easy. And I'm not gonna prove this unfortunately because the proof is not very intuitive, and I find sometimes the proofs just end up confusing people. Plus, I don't actually remember it. Um, but basically, here's the thing: the expected value of two random variables, and this might not mean much yet, but it's you can split it up into the two variables basically like this. The expected value of say two random variables x and y is expected value of x plus expected value of y. Now, how is this helpful?
Wait, shouldn't it be the product of both the?
No, it won't be. This is different. Like we're saying that say x can the average of x. Let's take an example, right?
Oh, so like so 50 times the head will come and like so both like head and tail they totally come 100 times. So like 50 plus 50 will give 100.
Not like that. No. We can't split it like that. You need to be able to add two expected variables to get those two. But I'll come to that in a moment, right? So let's
Shouldn't
take
X
the
and Y be
example of this.
independent here?
It's not necessary.
Ah, fine.
X and Y need not be independent at all. They can be anything actually. So they need not be independent.
Yeah. Fine.
Need not be independent. That means these two events need not depend on each. They can depend on each other. They don't need to depend on each other. It doesn't matter. Okay, so let's take an example. Let's say you roll two dice, right? Let's say you roll two dice, 1 to 6 and 1 to 6. Say, what is the average value of the output? Like of the sum, right? Of the sum of the numbers. You can get values from 2 to 12. So what is the the expected value of the output?
I didn't understand the question. Can you repeat it?
You roll two dice, right? Both of them from 1 to 6, right? Then regular dice, and you get some value, right? Which is basically the sum of numbers.
Yeah.
So what is the expected value of that?
Oh.
We are rolling simultaneously.
Yeah, it doesn't matter. Simultaneous, not simultaneous. I mean, the
Okay,
dice.
so here the random variable is sum of the two random variables here.
Yeah.
Okay.
I mean, you could calculate this the long way. Like you can do 2 into 1 by 36 plus 3 into 2 by 36 because they're like 6. The probability that you get like 1 and 1 is 1 by 36. The probability that you get 3, which happens in 2 is 1 and 2 and 2 and 1 is 2 by 36 and so on. You can do that, but instead you can just sort of here I'm basically asking you for the expected value.
So we can use linearity of expectation.
Right. And you can just sum the expected value of the two dices, right?
Yeah.
Here,
So for example, to get 5, it's like 2 plus 3. So 1 by 6 plus 1 by 6, 2 by 3. Oh no, wait. There are more.
That's a long way. That's a long way. You don't need to do that though because you can use. That's a long way of calculating expectation. By linearity of expectation, what I mean here is you can say that the expectation of the first dice plus the second dice is the expectation of the first dice plus the expectation of the second dice, and we know that the expectation is just 3.5, right?
So the answer should be 7, right?
That's it. Yeah.
Okay.
This
Like
3.5
in
is
this
what-
case, both the die have the same expectation.
right. Yeah, they have the same expectation.
Okay.
Did everybody get this? The answer is just 7 because you're just summing up two dice. I mean, yeah, this is like doesn't feel natural, or it's almost like magic. I think you can just sum up this 3.5. This long calculation that you might do, that ends up with 12 into 1 by 36, and you just calculate this value, you'll get 7, and you can just say sum 3.5 and 3.5 here. Okay, let's talk about the coin example now, right? I mean, I need you guys to like stop me if you're not understanding something. I can explain anything again. Right? Yeah. So let's just do the coin example. Ha ha ha. Let's just do a coin example. Um, yeah, so we have 100 coins. Now the expected number of coins. So this is what we're gonna do, okay? How we're gonna split this into a sum is we're gonna say the expected number of coins, right? This is what we want, the number of coins, right? And where our we want e of x, where x is the number of expected number of heads or whatever, and we're gonna split this into a sort of I1 plus I2 plus till I100, where I1 is equal to 1 if this is an intuitive concept. I'm just giving it a variable to work with. 1 if the coin is heads, 0 if it's tails, right? And so can you guys see that why this x is defined like that? I mean, it's basically number of coins, right? So if all 100 coins are heads, then all of them are going to be 1 1 1 1 1, right? I'm just basically defining these. These are called indicator variables. So basically, they're going to be 1 or 0.
So x is the sum of all the so I1, I2, all the way up to I100.
Naturally, right? Because x is basically counting the number of coins, and each of these coins is 1 if it's heads and 0 if it's tails.
Yeah. Okay.
So if there's the first 50 coins are heads, these first 50 variables are going to be 1 1 1 1, and the rest of them are going to be 0. So naturally, x is also going to end up being 50. This is a very natural definition, and so this is how, and we can write e of x as e of I1 plus e of I2 and so on till e of 100, I of 100, because of linearity of expectation. We can just split it like that, right? And now, can anybody tell me what e of I1 is?
Half.
Half, because it's 1 and 0, 1 half the time, and 0 half the time. So there's just half into 100, and that's 50. It's like a minute, like it takes 10 seconds to solve this way, like if you know linearity of expectation, right?
Yeah.
Is this clear,
Yeah.
like, for everybody? Yeah. We will do a bunch of examples until this becomes like a little more clear. Don't worry about it. Okay, yeah. So there are like a bunch of examples in the book Otis excerpts that I'm gonna use now. So I think this is a nice question. So say you have, like, I don't know, 2020 babies in a circle. And at random each baby pokes either the one to the left or the one to the right. Okay.
What are the circles?
Babies.
The circles are supposed to be babies, I think. I mean, I'm too lazy to try and draw. Like,
It's fine. It's fine.
It's like the top view. Okay, you could see their heads. Oh yeah, I'll repeat the question again. Okay, so they're like 2000. These are like 2020 babies. They're all like sitting in a circle. Yeah. So at random they poke at the one to the left or the one to the right. They're the baby to the left or the baby to the right. They can only poke the one to the immediate left or immediate right. Um, so you need to find the expected number of babies that are poked. Like a baby can be poked by the one on the left and on the right, or cannot. Like there's a chance that the baby is not poked at all.
So one baby can poke both the adjacent.
No, only one baby. A baby can poke only one other baby,
Okay.
either to the left or the right, and the
So,
baby will poke a
like-
baby either to the left or to the right.
So if like
Yeah, it has two options, but it can do only one thing.
Yeah. Go ahead, Saptarishi.
yeah, so like there's a baby, so he can poke any of the two adjacent ones, right?
Right. He will. A baby will poke one to the left or one to the right.
Okay, so what is the final question?
What is the expected number of babies that are poked?
Oh, okay.
Like, it is possible for all the babies to be poked. Actually, here's a fun side question. Okay, it's not that fun, but what is the least number of babies that will be poked?
Half the babies.
Yeah, right. I mean, I think so, yeah. Is that true?
No, we can poke like 1/3 is also possible, I guess. 1/3. Like
No,
take
the
it.
probability that a baby won't be poked is 1/4.
Correct. Go on. I don't think it's yeah. No, this is just a side question. The actual question is, what is the expected number of babies that are poked? You can do the same technique that we did for the coin problem. I'll give it like a couple of more minutes. Expected numbers that are poked, but you can also find not poked. That's okay. They will naturally sum up to 2020, right? The expected number of poked and not poked will sum up to 2020.
Is it 1515?
1515. Yeah, basically that. Correct. That's it. Yeah, so let me just solve this question. It's not that difficult. So I think, I'm not sure.
Wait, can I explain it?
Yeah, of course. Please go ahead. Yeah.
Yeah. So, for one baby, it can either be poked by the baby on its right or left. So, like the probability that it won't get poked is like 1/2 into 1/2, because like the other two babies can choose to poke the babies on the other side.
Correct,
So,
correct.
so there's totally 1/4 probability that a baby won't be poked. So, totally 1/4 probability. So you have to divide 2020 by 1/4. So that's 505. But we want to find out like how many babies will be poked. So then a 505, so 2020 minus 505, or 2020 into 3/4, which is 1515.
That's it. Correct, right? It's just 3/4 into 2020, because that's for each baby, the probability is 3/4. That you can split it up into indicator variables, or you can just directly say it's just 3/4 into 2020, right? Did anybody not understand the solution? Because it was explained very well. Anybody not understand it? No? Okay. So let's move on to the next question. Another hopefully not too complicated question. Which is just, again, we're just doing at this point questions that are going to directly ask you the expected number of something. So, okay, so here's another question, which is simple. You have like 2013 variables, and for each variable, we randomly pick its value as something from 1 to 2013, right? So, like, it's possible for all these 2013 variables to be 2013. It's possible for like only a few of these, like all. It's possible for A1 to be 1. Like, basically, for each variable, we pick a value from 1 to 2013 independently of all the others, right? Your question is to find the expected value of number of distinct numbers in this set. Did everybody get this question?
No.
Okay, I'll explain again. So each of these variables, we have like 2013 variables, or say we're picking a set, right? So we're basically going to pick numbers from 1 to 2013 times. Okay. And like, for example, a set could consist of 1, 2, 3 till 2013, or a set could consist of 1, 1, 2, 2, 3, 3 till 20.
So repetitions are allowed.
Repetitions are allowed, basically. That's it, right? We're picking 2013 numbers from the set 1 to 2013 with repetitions allowed. Okay. What is the expected value of number of distinct numbers in this set? Or did you get it now?
Is there a number of repetitions of 1 equal to the number of repetitions of 2 or something like that?
Nothing like that. It can be anything.
Okay.
So what's the final question?
Expected number of distinct numbers in the set. Like, for example, there are 2013 ways in which you can have only one number, which is basically selecting each number 2013 times. There's exactly one way in which you can have
all 2013 distinct numbers. Yeah.
All 2013 distinct numbers. So what is the expected value of the number of distinct? And the answer doesn't look good, I think.
2013 factorial by 2 raised to 2013.
Can you say that again?
2013 factorial divided by 2 raised to 2013.
No, isn't that summation not factorial?
Is it 1000?
I don't think that's the answer, if that's what you're saying, huh?
Is it 1007?
It's not 1007.
Okay.
This answer doesn't look good, right? Like, yeah. Take your time and split it up using linearity of expectation. Tell me what you get.
I haven't calculated the exact answer, but is it like we first choose like some x numbers from this 2013? So 2013 choose x.
Hmm?
Now we like find the number of ways such that these 2013 numbers are filled with only those x numbers, each being used at least once, and then we sum over all x and divide by 2 to the power 2013.
Um, can you repeat that? I'm sorry. Like, can you just say that again?
So we want the number of distinct numbers. So we first pick x numbers from 2013.
But like, that's not how we are picking, right? I mean, I'm just asking for the expected numbers when we picked each of them randomly.
Yeah. So I'll divide by the probability. Like I'm just forming the number of sequences and calculating the number of distinct numbers in each sequence.
Okay, right. Go on.
Yeah. So we first select x numbers from 2013. Like
Mhm.
I'm not selecting from A1, A2, so on till A 2013. From these 1, 2, 3, 4, so on till
Mhm.
2013. I select x numbers
Mhm.
and then I fill this sequence with those x numbers only. And I
Okay.
find the number of sequences.
Okay, you can do that. Yeah, what you're saying is correct. You can do that. But like, it's long, I think. If you don't use,
Yeah.
and the whole point of linearity of expectation is that it makes our job very easy. So you can like try using linearity of expectation, but you can use that too. What you're saying. Try calculating that.
So like there can be 2013 distinct numbers, or there can be 2012 distinct numbers, or they
Correct.
can be up to one distinct number, right?
Correct. Yeah.
Yeah, so shouldn't we just add it and then just do by 2013?
But you can't do that because it's this a weighted average, because it's not equal that there's not like an equal chance that there are 2030 numbers and that there's one distinct number. For example, let me see. There are 2013 ways to get one distinct number, right?
Yeah.
But there's only one way to get 2013 distinct numbers.
Oh, okay. Yeah, yeah. Okay.
You get what you're saying? Yeah. You
Okay.
need to like wait. It's a weighted average of with the probabilities, like expected value. Like it's just not just an average.
Okay.
Yeah. We'll maybe like start in like 1 more minute. We'll give it 1 or 2 more minutes. It's not too difficult. I think just split it up into each number.
So I'm just giving it a little bit of a guess. So is it like 1 into 2013 plus 2013 choose 1 into 2012 plus 2013 choose 2 into 2011?
I'm not sure. You can do something like that, right?
Yeah.
Can you say that again?
So
But we
like
have to first define the. Go ahead. Go
you
ahead.
yeah, so like 2013 ways of choosing one distinct. So that gave me the idea. So like we can do like 1 into 2013 plus 2013 see 1 into 2012.
Is this correct?
And yeah.
Uh, 2012 ways. So you're saying that I don't think this is true actually.
Okay. Yeah, I'm not sure.
Yeah. You can check, but this is not like the number of ways you can choose one distinct number. I don't think the number of ways you can choose two distinct numbers will be 2013 C. 2. Yeah, actually, I'm not sure what RVS is. Okay, you know what? Let's just solve this question. So I want the expected number of distinct numbers in the set, right? Distinct numbers, and just like the the coins or whatever problem, I'm going to split this up into indicator variables. Oh, right. Okay, RV is a random variable, right? Okay. Do we have to consider the cases where all are not distinct? Yes. You have to consider every case possible and take the average over all of them, right? So, yeah, where was I? Yeah, so the expected number of distinct numbers. So let's set up like an indicator variable for each. I'll talk about this an easier way too, but let's just do the linearity of expectation. Let's just to be clear about it. So let's set up an indicator variable for each number, right? Where I1 is 1 if 1 is in the set. It's in some number. It can be multiple times or one time, but if it's in the set, this is 1. And it's 0 if it's not there, right? And so this will obviously be equal to this. The distinct numbers will be equal to this indicator variable thingy, because if they're like if all of them are there, then all of these are going to be 1. Is by definition, right?
Wait, I actually didn't understand what I is here.
So I1, I'm defining a variable. I'm saying that the number of distinct. So I'm setting the random variable x, right? Our variable x, which is basically the distinct number of elements. Our answer. That's what it's asking. We're asked to find ex. So that's the x I'm talking about, and I'm saying that x is equal to I1 plus I2, and I'm defining I1 such that I1 is equal to 1 if 1 is in the set. Okay, and it's 0 if 1 is not in the set. I2 is equal to 1 if 2 is in the set, and it's 0 if it's not in the set, right?
Yeah, I got it.
And x will be equal to I1 plus I2 and so on, because that's what x definition is, right? If all of the numbers are in the set, then x, which is basically the number of numbers, has to be 2013, and all of these are that's what's going to come out, because all of them are 1, right?
Yeah.
And because we're basically asked for the expected value of x, the expected value of the number of distinct numbers, we can split this up as E of I1 plus E of I2 and so on. So, and all of these are going to be equal, right? All of the numbers are going to be equal. So let's calculate this. What is the expected value? What is the probability that a number 1 is in the set? Right? Can anybody calculate that? What is the probability that 1 is in the set? Or
1 by 2013.
1 by? That's 2013. Not true.
Okay.
Can anybody give that? Okay, what is the
probability?
2013
by 2012.
So find the probability that 1 is
2012.
1 is not. It's a like a JE question.
Probably 2 raised to 2013 minus 2 raised to 2012 over 2 raised to 2013.
Okay, can you repeat that?
Like 2 to the power 2013 minus 2 to the power 2012 over total.
Yeah. I don't see why you're doing 2 to the power. Like, I don't think this is correct.
Oh, sorry, wait.
Like, this is not head or tails, right? We're picking.
Is it 2013 to the power 2013 minus 2012 to the power 2013 upon 2013 to the power?
Something like this, yeah. Can you repeat that?
Minus 2012 to the power 2013
Hmm?
divided by 2013 to the power 2013.
That's it. Right?
Basically 1 minus this thing.
Yeah.
No, it will be this thing, right? Is it not?
No, 1 minus, he said 1 minus 2012 to the power 2013 upon 20.
Yeah, yeah. Oh,
Calculate the
right.
probability
Exactly.
like that and just subtract it from 1.
Yeah.
This. And the answer is just like if the expected value is this, if I1 is this I1, no? I1 will simply be the because we just need to find the probability that it's equal to 1. You know? Can anybody see why I1 is this?
Yeah, actually, I didn't
Because
understand how we got that thing.
which thing? This thing? Yeah, okay, I'll explain that. So basically, so let's say for each of those numbers, what is the probability that okay, let's calculate the probability that one is not there in this.
Yeah.
Okay. What's the probability that one is not there in this? It's 2012 by 2013.
Yeah.
This same thing, right?
Oh,
And the
so
probability
so
that one
I just
2012 by
lost my network connection for 1 minute. Can you just repeat?
wait, oh yeah, sure. So right, so I'm basically saying that. So what's the basically we're trying to calculate the number of ways in which one is not there in the set, okay? Or is there, which is basically amount to the same thing. You can subtract from one.
Okay.
So the probability that one is in the not in the first one is 2012 by 2013, the second one 2012 by 2013, and so
so
on and so
totally it's
forth.
1 minus 2012 by 2013, the whole power 13.
2013, correct. So this is the probability that one is in the set. Okay. So, or in other
Yeah.
words, this is the probability that one is in the set or that I1 is equal to 1. Right?
Yeah.
This is the probability that I1 is equal to 1. In other words, and the probability that I1 is equal to 0 is this. Right? Is this clear?
Oh, right. Yeah.
No, actually, I didn't get this.
So, did you understand the 2012 by 2013 part?
No, that's what I didn't.
All right. So, what is the so we're basically looking at say you have you're basically choosing 2013 numbers, right?
Yeah.
So the probability that one is not in the first one is 20. So basically, we want to find the probability that one is not in the set, or if one
Okay.
is in the set, same thing, right?
Yeah.
Like we need to calculate one of these things. Now, what is the probability that one is not in the first one?
So like a 1 is not there in the set.
One is not in no. One is not the first variable. Like the first variable, we're choosing randomly between 1 and 2013. So
Okay,
what
so
is
that
the
is 1 by 2013.
yeah, or the probability that one is not in the
Okay,
set
so
is
2012 by
2012.
2013. Okay.
Right. The probability is the same. It's the same for the second variable and so on.
Okay,
Right?
so we multiply, so it's 20 to the power 2013. Okay, fine.
Right, because the probability that one is not there in any of them is the multiplication of all of these. So the
Okay.
probability that one is not in any of these means that I1 is 0. That's how we define the indicated variable I1, that one is not there. So this is the probability. And the probability that one is in the set is this. Right?
So we need to
Yeah.
add like both the probabilities and divide it by 2.
Oh no, this is the what is expected value? Expected value of I1 is going to be, remember, it's summation of probability into the value, right?
Oh,
So
yeah.
so it's going to be this into 1, that stuff into 1 plus this into 0. So it's basically going to be this.
Oh, yeah.
Can everybody see that?
So we need to
Yeah,
so for that's for so if it's for 1, then it holds good for each number. So you have to multiply by 2013.
yeah, this multiplied by 2030 is the answer. That's it. Did everybody get this? Like some idea at least?
Yes.
Yeah.
Yep. Basic. Okay. Now let's just do this an easier way. Like explain the same thing in a slightly easier way. Basically, what we are
So
saying
our
is that
final answer will be 2012 by 2013 whole to the power 2013.
Oh no, this will be our final answer.
Yeah.
This, yeah.
Yeah. Okay.
Yeah, so let's just explain this simpler. Um, so our expected number of the total, of the number of distinct numbers is sort of 2013 into the probability that any single number is there, right? It's 2013 into the probability that any single number is there. And the rest of the thing, once you realize that, the rest of the calculation involves calculating what the probability that any number is there, like one is in the set is. And hopefully, with a little of practice, that will come easily, right? This calculating this number is easy, but that's like, think of it separately from the linearity of expectation part. The hopefully you should realize why we had multiplied 2013 by this, right? So does anybody have any questions? No? Okay, let's move on then. Okay, let's do another classic example. Let's say there are n people at sitting in a circle, or it doesn't matter how they're sitting, right? Let's say n people, and all of them have name tags. Okay, we'll do this is the last expected value, and then we'll move on to some other Olympiad problems. So all of them have name tags, their own name tags. Then the name tags are like jumbled in a pile, and each person takes out a random name tag. Okay, what is the expected number of name tags that comes back to their
So how many
actual
people
owner?
are how many people are there totally?
Let's say 100.
Okay.
What is the expected number of name tags that come back to the right person?
But how are they arranging the name tag?
Randomly, right? I mean, everybody has their own name tags, and then it's all put in a pile, and everybody takes out a random name tag.
Oh, okay, fine.
It's just one, right?
Yeah, that's the answer. One is the answer. The
Like you
expected number is. Yeah,
so
go on.
okay, so it's 9 n minus 1 factorial n times, then you just divide it by the probability, which is 1 by n factorial. Which
I
is
didn't get you. No, it's not that complicated, right? So what's the probability that any single person gets their name tag back?
100th.
100th, right? And that into 100 is the answer. Can everybody see why this is true? We can set up indicator variables again.
Yeah. What is the what will be the random variable here?
The random variable will be x, which is the number of name tags, basically. The number of name tags that comes back to the correct person will be the random variable. That's what's changing, right? Because each time we're calculating the expected number of name tags that come back to the right person.
But
the indicator random variable would be 1 if the right person gets his name tag,
Yeah,
and
correct.
it is 0 if
One,
it does
so
not.
like I1 will be 1 if the
but is it
first person gets
necessarily
it.
true that it will be one by like the number of people who I mean the probability that you get your own name tag is 1 by 100, because like there'll be one person picking it first, and then so the probability would reduce.
Oh, think of it like this, okay? Think of it like this. It doesn't matter what order you're picking, right? Because the probability that you take say the 5th name tag and the 20th name tag is the same, right? Because it's equal. They're symmetric. There's no difference between them.
Oh,
Like,
yeah.
The way you're picking, yeah, it's sort of unsymmetric towards the people picking first in some sense, but like everybody has the same chance of getting some random name tag. Can you see that?
Yeah.
Or you can change the question if you're uncomfortable with that and say everybody, sort of puts their hand in a pile and takes out their name tag and takes out some random name tag at the same time. The order they're picking doesn't really matter here.
Yeah, okay.
Yeah, so basically,
but you see that this result is also interesting because it shows that expected number would be just one. So like
yeah,
on an average, only one will get its own name tag. out
Correct.
of 100.
It's interesting to think about that, right?
Yeah.
The average number is like only one. And in general, another interesting thing about this is 100 could be anything. The probability will be 1 by n and the number n, so it's always going to be 1.
Yeah.
Even if you have 1,000
Yeah, right.
people, the answer is going to be 1, which is like super interesting. And if you had to
I
do this
just-
question, yeah.
So I was saying that say you have 100 people here, then the probability, like if you fix one person that he gets the name tag, then the rest can be like permuted in 99 factorial ways.
Okay, go on.
So you sum this n times and divide it by 100
You
factorial.
we can't get the answer like that.
Wait, you
Because
can.
because for one thing, what you're doing is you're fixing one person to get the name tag, which is not necessary. Nobody,
Yeah.
it's possible that nobody gets the name tag, right?
Yeah, right. It is also possible.
And
Because
it is also possible
this is
that
just
two
speaking
people
about the
get the name
average.
tag. Yeah, it's possible that 2 people get the name tag or 3 people get the name tag.
So this can also
Exactly.
be like thought by dearrangement also.
You can do that. You could. That's the long way, though, right? You need to calculate the whole dearrangement and do the whole.
Yeah,
bit.
so basically we need to do 100 factorial minus factorial 100, I think.
I'm not sure. You can do the calculation, right? Basically, I'm asking you expected value of x, and you can do that summation. How we define this is probability that some x is equal to some x into x, right? You could sum the probability, find the general value.
Yeah, so to
of,
find,
yeah, you can sum this up and get it. But linearity of expectation gives the answer in like 10 seconds.
yeah. So
You can do the
irrespective,
summation.
yeah, so like whatever value of n we take, it's always going to be 1.
Correct.
Yeah, okay.
You can do the summation. You can find the probability that we get, I don't know, two people get their name tags back, 3 people get the name tags back, etc. And then you can put the general expression here and then do the summation. But like this is a really simple method. Linearity of expectation gives a really simple answer. So is everybody cool with
Yeah.
this? Yeah.
Yeah.
Okay, so let's do an actual question in which we solve stuff. Like instead of we're solving stuff, but a question that doesn't directly ask you what expected value is. What expected this. So, oh wait, what was the question? I completely forgot. Okay, I think this was the question. You have 6 in an olympiad, right? Say the IMO. You have basically you have like 200 people participating, right? You have 200 people participating in the IMO, and you have 6 questions. Each question is solved by at least 120 people. Okay? Each question is solved by at least 120 people. You need to prove that you will be able to find, and okay, this is a slight jump in difficulty, I think. I'm not sure, but you should be able to get it. You need to prove that you will be at least be able to find 2 people, some random 2 people. There exists some 2 people such that together they have solved all 6 questions. Is the question like absolutely clear?
Together they solve two. How many questions? All the 6 questions.
Yeah, like every question is solved by at least one of them.
Okay, so like, can we include cases where both of them solve the same questions?
Yes, that's okay.
What, there are 200 people, and then what?
There are 200 people. Each question, each of the 6 questions is solved by at least 120 people. Okay? You need to show that we can find 2 people such that together they solve all 6 questions.
Okay, so
like the right place
in
to
this
use
it
it.
is
Yeah,
also
go on.
included that the first person might solve 2 questions, and then the second person have solved 4 questions, then both sum is 6.
But like they should have solved, like then they should have solved
The
distinct
question should be like unique.
Yeah, in that case, because they like basically like all 6 questions should be solved. So it can't be like one person solves questions 1 and 2 and the other person solves 1, 2, 3, 4. Like because nobody has
Okay.
solved 5 and 6.
Yeah.
You need to find 2 people such as all 6 questions, and you need to show that whatever the case, this is always possible. Like It
So we
doesn't
need
matter.
to prove that like there is always two such people such that they've solved all 6 questions.
Correct. And nice. Sevenwick, you can sort of speak, right? You don't need to raise your hand. You can open your mic and speak because you've raised your hand. Sevenwick. Okay. Yeah, so let's just try this question for a while. Okay, and just because this is your first non-expected, here's a small hint of sorts. Try to find a random variable x, or a certain expected value, such that if you when you find it, you can get the answer of sorts. Like try to find something like that. Yeah, don't apologize. It's okay. And if you guys get like progress or ideas or something like that, or if you have an idea for this, you can speak up.
So I think we can consider, like we, for the sake of contradiction, we assume that there exists no pair such that they solve all 6 questions,
Okay.
and then we try to prove that any of the question cannot be solved by 120 people.
That's a nice approach. You can try that.
And to
Let me
start
know.
with, like the probability that a person has solved any one question is 3 by 5.
Oh, correct. It is. Yep.
Can you
There
repeat the
are-
question once again?
So you have 200 people. The You know what? Let me just check the question once. Yeah, so you have 200 people, and the probability that no, sorry, give me a second. I'll repeat the question. Yeah, so I'll just read out the exact question. An Olympiad has 6 problems and 200 contestants. Each problem is solved by at least 120 of the contestants. Each problem. Okay. Prove that there exist at least 2 contestants such that each problem is solved by at least one of them. That means there exist some 2 contestants such that together each of the 6 problems have been solved by at least one of them. Is it clear now?
Yes, thank you.
Awesome.
Okay, so probability of solving one question is 120 by 200, which is like 3 by 5. So
Probability of who's solving one question?
like one person.
Okay, go on.
So the number expected value of, like, the expected number of questions solved by one person is 18 by 5, which is 3.6.
The expected number of questions that somebody solves is 3.6. Okay.
So now, by linearity of expectation, there exist 2 people which solve 7 questions in total. Like it's not necessary that they are unique here.
Okay. There's no linearity of expectation here, right?
Like expected value of person 1 plus person 2 is equal to expected value of person 1 plus expected value of person 2.
Okay, right. So they expect right. So that way, okay.
Yeah. So now we have to prove that, uh, like, yeah.
As a matter of fact, you can say the value. This value is up to 8 because if the expected number of problems that a student has solved is 3.6,
Yeah.
and since the answer can only take the number of questions a student can solve can only be 1, 2, 3, 4, 5, 6. You
Mhm.
can say that the number of things a student has solved has to be at least 4 because it's more
Oh.
than 3.6. No?
Yeah. Fine.
Yeah, so you could say that there'll be at least one student who has solved 4,
Yeah.
right? Or something like that, but
So
this
why
is
can't
not
it be
useful.
3 each?
That can happen too. I mean, it can do that. You can do that. I'm just responding to what Pranav said, but I don't think this directly gets you anywhere.
Yeah, okay.
Like I'm just responding to that. Yep.
Okay. Yeah. So now what we do is like, there exists one person which solves 4 problems.
Right.
Yeah. So let it be person 1. So person 1 solves P1, P2, P3, P4. And we
Okay.
need to prove there exists a person which has solved P5 and P6 at least.
Okay.
Yeah. Which seems doable, I guess. From left.
You could try that. Sure, yeah. Go ahead.
Give me a minute.
Yeah, if no one does both, then you can't have 120 solves on any of those. Okay, about 40%.
Yeah, what you're saying is true.
overlap.
Give me 1 second. So at least one person has solved 4 questions. Let me just try this out. Again, what's the probability that a person has solved, say, question 1?
I think it's
3 by 5.
Right. Thank you. So this is at least 4, and yeah, I think this works actually. Why haven't I seen the solution? Yeah, this works, I think. Did everybody get the solution that was just said?
Yeah.
Wait, I didn't get it. Can you repeat?
Okay, so what's the probability that oh wait, give me a second. Yeah, so what is the probability? What is the first we want to find the expected number of questions one person solves, right?
Yeah.
And the answer will be
3.6.
3 by 5. Yeah, this 18 by 5, right? That's 3.6, right?
Yeah.
And if the expected number of things a student solves is 3.6, then at least some person has solved more than that. Like
Yeah.
equal to or more than that, because
Yeah,
it's the average, right? Somebody has to have more than the average. So somebody has solved at least 4.
Yeah.
And if say the other 2 questions that are left out, and we can also say that given any 2 questions, there'll be at least one person who has solved both of them, right? Because there are like 120 people who have solved each question, and like only
It's
200.
like 3.6. So how is it like at least 4?
Because
This has to be more than 3.6.
because 3.6 is the average, right?
Yeah.
And the value that this thing we're talking about, the number of questions a student solves, can only be either 1, 2, 3.
And people
4.
can't solve exactly 3.6 because it's not a whole number.
Yeah, that's what. It's not an integer, but
Yeah, so like that, there has to be at least one number more than the average, right?
yeah. Okay.
So
yeah, just have to. Is it like rounding it off, or is it like a ceiling function kind of thing?
it's not rounding it off. We're basically saying that a number should be more than
Yeah, this
3.6.
is rounding.
This is not like rounding off exactly. This is
Like, we would have got 3.4. It would have still been 4 only, right?
right. But like rounding in the sense, we're not exactly rounding
Yeah,
here.
that's what I was
We're
like.
using the fact that the answers can only be integers, natural numbers,
Yeah.
right? So and if that is true, then this has to be at least 4.
Yeah.
But like we're rounding off. Practically speaking, that's what we're doing.
But
Yeah, like there must be something greater than 7, or else you can't get 7 point.
Can you say that again?
Like you have to have some number greater than 7, which is also an integer because you have expected value 7.2.
Right. But that doesn't give us much. Yeah, anyway, so because there are like 120 people who have solved and only 200 students, so given any 2 questions, there's at least one person who solved like any 2 questions,
Yeah,
right?
this is PHP.
These 2 combined give us our answer. Did everybody get this solution?
By the way, there is another method to finish also. Shall I tell?
There is. Yeah, go ahead, please.
Okay, so we know that there exists at least one person who has solved 4 questions. Now
Right.
we find the minimum number of people who have solved 4 questions.
We find the. Give me a second. 1 second. Go on, please.
Yeah, so we try to find the minimum number of people who have solved at least 4 questions. So let the number of people who have solved 4 questions be x.
Okay.
So the total number of questions solved will be 4x at least. I mean, like in the optimal case, 4x plus 200 minus x into 3.
Okay.
Yeah, so
I see what you're saying.
yeah.
Okay, go on.
So that comes out to be, that gives like x is at least 120 and we are done by that.
But then there can be some overlap, no?
How?
Between like if two people solve 4 questions, there can be overlap.
Yeah, so no, my point is like there are at least 120 people who solve 4 questions. That's clear, right?
Yeah, sure.
Yeah. So now assume that there is a overlap. So all 120 solved first 4. So like other 80 are there which have solved P5, P6, something like that. You know?
You can try that, but that's not like still rigorous. You can see that, no?
Oh.
It's not like fully rigorous yet, what you're saying. Yeah, anyway, I'll give another solution, which is like, I think pretty nice. So what is the probability that, say, pick 2 random contestants? What is the expected number of questions I'm going to calculate that they miss together, right? And the answer is that like
He said 1 minus 3 by 5 the whole square.
Right, it's 4 by 25. The probability that they miss a certain question is 4 by 25, right? It's simple. The probability that one person misses one specific question is 2 by 5. The probability that they both miss the question is 2 by 5 square. And the probability that, so it's basically what, 2 by 5 square. Right?
Yeah.
And the probability that, now the probability, this is the probability that they miss a specific question. So the expected number of problems that both of them miss, and you could set up indicator variables to do this, is 6 into 4 by 25 because there are 6 problems and for each of them contributes 4 by 25. Well, this is 24 by 25. So we're basically calculating the expected number of problems that both of them miss, and this is less than 1. In other words,
it's 2 by 5 whole square, but like it's not 1 minus 3 by 5 square, right? It's 1 minus 3 by 5 whole square.
Right. Oh, I'm sorry. Did I agree to the wrong thing? I'm sorry. Yeah.
Yeah.
Oh, yeah. Just to be clear. Yeah. So yeah, the expected. So can everybody see why 24 by 25 is the expected number of problems that some 2 random contestants will miss? They can miss some 3 problems. They can miss 4 problems. They can miss 12 problems. But there has to be at least something less than 24 by 25 for the average to be 24 by 25. So there has to be at least one, group of people who have a 0 miss. Can everybody see that? Yes.
What is this 24 25?
24 by 25.
Right. So let me explain that again. So 24 by 25 is the probability. 1 second. 24 by 25 is the probability that 24 by 25 is the expected number of
misses.
Expected number of misses among 2 people, like the expected number of misses together.
Yeah.
Okay, and that's true because 4 by 25 is the probability that some specific problem is missed by them. So the expected value will be 6 into 4 by 25. And you can check this, like check that what I'm saying is fully proper. Later on, try this problem and check that it is fully proper. Right?
Oh,
and
so you are saying that.
Yeah.
So you are saying that this expected number of misses is less than 1. So this means that there must be 2 people that cannot together miss any problem.
Right, because we're calculating the average rate of some misses. Like some 2 specific people missed all 12, some 2 people missed 3, some 2 people missed 4. But like if the average is supposed to be 24 by 25, then somebody has missed nothing. Some 2 people have missed nothing.
Yeah, exactly.
Did everybody get this? Yeah.
Yeah.
Hopefully we did. Yeah.
Yeah,
Yeah.
got it.
Nice. Okay. Let's go back to the problem that I'd given at the start. Oh wait, I've been going bigger and bigger, have I? Okay.
Yeah.
Nice. Okay. Okay, so everybody try this question for a while. Okay, so I'll just explain the question. Um, so that like in a class, there's like certain number of boys and certain number of girls, and each boy is a friend with at least one girl, right? Show there exists a group, right, of at least half the students. That means you select a number of boys and you select a number of girls from this group, from the total class, and the total number of students together should be at least half the total number of students. Like the number of students in this group should be at least half the students. So there exists such a group. Inside the group, inside the boys and girls in the group, each boy is friends with an odd number of girls in the group. Inside the group. Right? So you need to show that such a thing exists. Did you all understand the question?
Yeah.
This? In IMO, you can have patience, yeah. Too bad that this Olympiad doesn't allow whatever. I can probably try to make like a problem set with some probability based questions. So basically, a common theme between this question and the last question is the fact that you're trying to show the existence of such a something. You're trying to show that something exists, and when you're doing this, you can use probability because probability we're not constructing something explicitly, right? Pranav, you have a lot of friends, I'm sure. Yeah. So there exist questions work well with probability because you know um, you're not trying to construct something. um, when you're using probability, you're not explicitly showing how to find something. You're just showing that, oh wait, something exists. Something greater than that would exist. Yeah. Oh, there was something else I wanted to say that I'm forgetting. Not in Boston, I'm in Bangalore. Dude, college doesn't start until September. Next September. Anybody has any progress? And basically, just as a tip, like when trying to approach something with probability, first set up whatever you're trying to compute the probability of trying, like take it in separate steps. For example, here ask yourself what expected value. Um, Again, I haven't started college. College starts in September, next September, right? A lot of time for that. Yeah. So ask yourself what variable, um, if you find the expected value of, can you find the answer to this question? Can you prove this question? Like that.
Can you repeat the tip?
I mean, I'm generally saying be organized. Like, ask yourself, what random variable do you choose such that finding the expected value of that random variable will help you get your answer. And then finally, keep your computation and the brain work separately. It's something that's obvious, but like we mess up the exam. Our brain
Yeah,
is
yeah,
not.
obvious, because if we are calculating expected value, we have to set up a random variable.
Yeah, keep the thinking separate between the two. Keep the calculation different. And this is different.
So there are more girls than boys.
There could be more boys than girls or more girls than boys. It can be anyhow. Oh yeah, another tip I was thinking about, right? So,
How can there be more boys than girls?
why not?
Like,
Did I miss something?
uh,
Yeah, because each boy is friend with at least one girl. Oh wait, they can be friends with the
But the
same girl.
same girl can be
Yeah.
friends of
okay.
many boys.
But at least, so there's at least one girl.
Right. Okay, sure. That's at least one boy too. Is that not necessary? Okay, I don't think that's necessary. Is it not? Yeah,
No,
sure, but
it's definitely necessary that okay, wait. Okay, it's
I
not
don't,
actually
don't
necessary.
worry about it. Yeah, this is like edge cases are not interesting here. But like, yeah, sure, there's at least one girl. Or there could be nobody in the class, but that's very boring. So we'll have a few people. Yeah, so you can make like a incidence matrix, which is something I wanted to initially cover, but I can do that in a different class. Basically, you could like, it's basically you can write like girl one, girl two here, and boy one, boy two, and you could sort of make a tick wherever. It's a way to organize your data and help you think maybe. And you could have done that in the previous question also, where you had like 6 questions. Question 1, 2, 3, 4, 5, 6, and participant 1, participant 2, and you can sort of imagine taking. You can't make a whole list, but like imagine taking and trying out things. Just like making these things will help you think. Make summations and think. That's what incidence matters. It just helps you think. That's all. It's a way of helping visualization. And you can try different cases.
So are we gonna solve it today or like?
Yeah, I'll solve this one today. And I think it'll be the last one. Yeah. I'll just give you like a one. You should like try the problem. Try to get the problem. Yeah. I'll give you like 1 or 2 minutes to explore the problem, and then we'll start. We'll start at like at 8:50. Oh, it's 8:17 or 80.
So the last question, we multiplied 2 by 5 whole square with 6, but we already like considered 2 people together, right?
Yeah. No, we're multiplying 6 for the number of problems. Okay, so I can do that properly in the meantime. Okay. So what I'm saying is that the expected number of give me 1 second. Yeah. The expected number of problems that x, right? Expected, where I'm saying that x is the number of problems that both of them missed. Okay. That is equal to I1 plus I2 plus I3 and so on. When I1 is the 1 if problem 1 was missed till I6, and I1 is 1 if problem 1 was missed, and 0 if it was not missed. Okay? And what is the probability that I1 is
I
1?
got it.
Yeah, okay. This is 4 by 25. So expected value of I1 is 4 by 25. In general, for an indicator variable, this should be obvious, but in general, for an indicator variable is something where, it's 1 if something is true or 0 if it's not. Ashok, go ahead. You don't need to raise your hand. Right? Okay, so it's 1 if something is true and 0 if it's not. So for such a thing, the expected value of such a variable is just going to be the probability that it's 1. Can you all see that? I mean, it's just going to be p into 1 plus 1 minus p into 0. Did you all just understand what I said?
Yeah.
Yeah.
Also, what was
Yeah,
the random variable?
What was the random? The random variable is the number of problems that two people missed. You know,
Okay.
like if one of them did it, it's not going to be counted. But if they didn't, you count. It's like if you put it this way, it hopefully the solution feels simpler. We're just calculating this random variable. We first set up this random variable, and the rest is just calculation.
Okay, so in the last question, the random variable was like the number of misses with two people combined.
Yeah.
Okay.
And we wanted to show that number could be 0. That's why we chose such a random variable. That's the motivation. We wanted to show that such a random variable could be 0.
Yeah.
Right? And then we just tried to show that we confirmed our suspicions.
Yeah.
In this case, find a similar random variable or something like that. Yeah. This is a more complicated question, the solution, the approach. Okay, so let's just try this question. The idea in this question is that, we have a bunch of text here, how do I motivate this? So basically, I want to show that, let's see,
Here it is a bit difficult to set the random variable, right? Random appropriate.
It's definitely harder. Yeah.
Yeah.
So what we're going to do is that instead of like randomly choosing, like here, in the previous question, we chose like a random group of two people together, right? We chose like a random group of some two people together. We did that. Here, I need to figure out what random group of people I'm going to choose, right? Because I need to choose like, if I'm going to apply expected value, I'm going to have to choose some random group of boys and girls and show that of size more than half, and show that, the condition of the problem will hold. But I can't just, yeah, go on.
I didn't get. Can you repeat what you just said?
In the previous problem, we chose like a random pair of two people and calculated the expected value of how many misses they have. Correct?
Yeah.
Here we need to also like choose some random group of boys and girls, right? That's what we need to do to find expected value.
So in the random group, there should be exactly half of the number of total students, right?
So what I'm going to do is that I'm going to choose a group in such a way that our condition holds, right? This odd condition holds. And then I'm going to make a random variable the size of the group.
Yeah.
And I'm going to show that the average of this has to be at least half.
Yeah,
exactly. Get this approach?
Oh, wait, can you repeat it?
Yeah, so I'm going to choose a group in such a way that our condition holds. Okay?
Yeah.
I'm going to make the choosing of the group random, but I'm going to choose it in such a way that our condition holds. And then I'm going to find the expected value of the number of people in the group and show that that number has to be more than half the people.
Oh, fine.
Did everybody get this?
Yeah, this is fine.
Yeah, like hopefully it's like sufficiently motivated enough, right? I'm just like using the condition we have. And how do we do that? Okay, so now that's the question. How do we choose a group as randomly as possible such that our condition holds. Anybody? And the idea is here is that you need to treat the girls and the boys differently because you know they're like on two separate parts of the table, so you can't choose just like put everybody together and choose a bunch of people. You can't do that because then the condition might or might not hold. So it's something. I'm going to do something simple. I'm going to choose a random subset of the girls. Like say for each of a girl, I'm going to coin flip and choose a random subset, and then I'm going to choose every guy that um, satisfies the odd condition for that subset of girls. Can everybody see this? Can everybody see what I'm saying?
Yeah.
Yeah. Okay. Can you now calculate the expected number of people in such a group? Obviously, the expected number of girls in this group is exactly half because now such a group will automatically satisfy our conditions. The way we are choosing it is we're only choosing the boys who who are friends with an odd number of girls in this group. So we're automatically satisfying the condition. Now we are going to find the expected number of people in the group. The expected number of girls
But
is just
suppose like the boy, like one boy, he's friends with like an odd number of girls totally, but then like not all of them are there in this half, then it won't hold good.
Yeah. So if that boy is only friends with an even number of people in the group, then we will not choose that boy.
Okay. Oh, so that's how we're choosing like the boys.
Yeah, we're choosing boys like that. We're choosing a random subset of girls, and in that subset, if a boy likes is friends with only a certain number of like an odd number of even number of girls in that subset that we chose, then we will not choose that boy.
Okay. Yeah, I get it. So then what about the other half? Okay, so only one half matters.
Or for?
No, so so when we take like half this half of the girls,
We're not taking half of them. We're like for every girl, we're choosing them with probability half. So it's possible that we might not take any of them.
So by dividing the total group into two, right? So like what happens to the other half? Like doesn't it also have to satisfy the same condition?
No.
So it's just only one half matters. Like only one half we need to choose.
Only one group matters. Yeah, the rest don't matter.
Yeah. Okay.
Okay.
Can you just move the board to the problem statement for one second?
Yeah, is that okay?
Yeah.
Can anybody use this to finish? You just need to calculate the probability. Guys? Like just calculate the probability that a certain boy. What is the probability that a certain boy will be chosen? Anybody? It's not that difficult.
Is it half?
Yeah, it's half. That's it.
Odd and even. Yeah.
Yeah, it's just either odd or it's even, right? Because like say
half.
with,
You said half.
Yeah, it's half.
Okay.
So for every boy, the probability that the boy is chosen is half, because let's say now you're talking. Let's say we are coin flipping the last girl, right? We choosing every girl with probability half. Now let's say the probability. Now let's say so far boy one has an odd number of friends in the girls chosen. Okay, then the probability that he gets chosen will be half, because the probability that the last girl is chosen is half. Get it? It's not very complicated. It's just like simple logic. It's either odd or it's even. So each boy is chosen with probability half. See, every girl is chosen with probability half, and we all chose boys in such a way that every boy is also chosen with probability half. That means, on average, the expected number of people that are chosen are half of them. So there is at least one group of people with more than half the number. Is this clear? I mean, at least like, do you guys understand it? Understand
Yeah.
what's going on? I mean, I know this might feel a little overwhelming. This is a pretty difficult question. Uh, but like, I just want to get you to get an idea about how probability is used. Did everybody understand this?
Yeah.
Yeah. This is the last problem
Yes.
that we
So
do.
after selecting the like, how do you select the random set of girls?
Coin flip. Each girl select with probability half.
Okay.
To choose all the girls randomly, like probability half. After you've chosen the set of girls, choose every boy who has an odd number of friends in the girls.
Yeah. So that is also half.
And then we can show that, yeah, the probability for each boy being chosen is half.
Okay.
And that's because, it's just either odd or even. He has either an odd number of connections or an even number of connections.
Okay, but then how do you finish? Can you please repeat that?
Yeah, so do you get that for every girl we're choosing with probability half, and every boy is also being chosen with probability half.
Yeah, I get that.
So in the group that we have, our condition is being met. This odd condition. We're choosing in such a way. We're choosing only boys with an odd number of friends. So this condition is automatically met.
Yeah.
And since we're choosing each person with probability half, every person in the entire thing, the expected number of people is half the number of people.
Yeah. Fine.
So that there's at least one possible group, because the expected number of people in such a group is half the total number of people. So there is at least one such group with more than half the number of people.
Yeah, got it.
Okay, so we basically this this is a really cute question, and this is a nice question. So okay, we're basically gonna this is the last problem we're gonna do. I can possibly make up a small piece set and send it your way. And these problems are you typically have to spend like much larger amount of time. When I tried this problem, I did not get it without like a couple of hints in a couple of days.
Yeah, you are right,
So where
because
is this question from? Like which exam?
Oh, this question is from a Russian Olympiad. This one. Uh, some Russian Olympiad.
Oh, okay.
I can send you the handout in which I found this. I'll give you a minute. You can choose. There are like other. I'll just send the handout here as well. I'll also send all the handouts that I used while preparing for this talk. But later in the Discord, or I can send it by mail if you're not in the Discord. But this handout was where I found the question, and the other questions you could try. Similar questions. Oh yeah, the other questions were in Otis except like I have actually a bunch of other questions like ready, and I thought I'd judge the audience and they'll go harder or easier. Yeah.
also this method is like an advanced method, so it essentially will require more time.
Yeah. It's not like it's like hard intuitively speaking. Yeah, you need a little practice with it. Mess around, go and mess around. Yeah. So I'll answer your question, Rohin. So can I just stop recording if there are any other questions related to the question? Anything? No. Okay. I'll end recording and then we can talk if you want.